interesting. That's all. Can I give this to Shahram?
Antonio, thanks very much. Okay, and we are bang on time as well. Fantastic. So we've got about another half an hour to go, and Antonio was talking about a load of themes there, but he also touched on NUIs, natural user interfaces to help doctors or even lay people make sense of these really complex pieces of anatomy. And we're going to finish the day by talking a bit more about NUIs. And believe it or not, Microsoft Research seems to know a little bit about NUIs. I don't know what kind of products spring to mind, but apparently they do. So that's what we're going to talk about in this last half an hour. So hopefully we're joined by Tom Rodden of the University of Nottingham. And he also, fortuitously, happens to be a co-author of a publication from Microsoft Research entitled Being Human, Human-Computer Interaction in the year 2020. Yeah, let's take a view there, Tom. That's great. So also joining Tom, let's have, two members of the Computer Vision Group, Andrew Fitzgibbon and Jamie Shotton. They're both here, so get you sitting over there. They are award winners from the Royal Academy of Engineering, the McRoberts Award. They won that this year for their contribution to the Connect Xbox 360 gadget device. And also Shahram is here as well. Shahram Izadi, who's a researcher in the Sensors and Devices group, so he's going to come up and join us as well. Also won a Technology Review Award for Young Global Innovators under the age of 35. So a whole load of award winners here as well. Have you brought your gongs with you or left those behind? So the form is, as I understand it, gentlemen, is that you're going to each show us, I think, a bit of video, and you're going to talk us through some of your research, and in some cases experiment on me as well. So I don't know who wants to go first. Tom, maybe.
I think I'm due to go first.
First in the running order.
Let's see what happens.
Okay.
Yeah. Should I be pointing this in a particular location?
Seems to have done something.
Okay, so NUIs. So this is the kind of image that most people think about now. They think about desktop, mouse and keyboards. In fact, one of the big questions is, so what happens when the keyboard and mouse disappears? But one thing that I want to say, well, what's new? So this image is from, as we may think, just after the Second World War. And the actual view of interaction there is given as a head-mounted camera taking images and then images projected onto the lenses. So the vision of interaction with computers in Vannevar Bush's paper didn't seem to centre around keyboards and mice. So it's rather strange that we have this kind of strange dominance of the keyboard and mouse, and I think that's one of the successes of it. The other thing that people often think about are the imagery that you get from films. I mean, this is the kind of classic imagery of, and what's really interesting in this particular scene is the kind of beauty of the kind of carved wooden ball that rolls down and captures all the image and people manipulate through it. And I think those are the kind of compelling, slightly technically led views that are at play here in these images. So I want to talk a little bit about some of those. So the other classic one here is Sixth Sense from Patty Mays, which allows you to project onto any surfaces using a Pico projector and make any surface kind of interactive. So as NUI is about allowing anything to be an interface. Well, some of the work that one of our PhD students at Nottingham did kind of explored this a little bit, and as a kind of art piece, decided to take the deformation and colour change that happens when you press on your finger and use a very simple visual tracking algorithm to generate and create a little pet rock. So there's a little rock that existed with a camera above the cage, and you could reach in and stroke the rock, and it would have a kind of oral interaction with you. And so this was kind of played with as a can anything be an interface. And one of the things that came out of that, certainly in the YouTube comments afterwards, was no, it shouldn't be. Not everything is actually naturally an interface. Some things are just objects, you know. They don't have to be interactive. So that's, I found that kind of interesting. The other one I want to talk about is well, so it's about sensing. I mean, there's quite a strong dominance And most of the technology you see about vision and video tracking has been what NUIs are about. So let's take something something natural then. So there's nothing more natural than breathing, you might imagine. So let's look at a little video clip which hopefully should play. Do I need to click?
Yeah.
Yep. Okay, so this is a ride that we built here at Nottingham, which took a bucking bronco and used a very simple algorithm and a chest strap to allow people to control the actual bronco based upon the breathing. So you would control your breathing, and the rate of your breathing would speed up or slow down the actual bronco itself. So there's a kind of feedback and control involved here, where you're doing natural control of your natural kind of body functions in order to stay on the ride. Okay, so this is very much a spectator piece designed to play with how people might think about interacting with these systems. So, but what's compelling about this is that interaction actually feels far from natural here. It's about taking an autonomic part of your body and trying to control your breathing. It's something that isn't actually that natural to do. And this, you know, another spin-off from this work with Brendan Walker, we've done a range of art pieces called Breathless. And so this is a breathing-based brace string. And just to give you some idea of how short a journey can be, a journey from a bronco to we've lost an image. Right. A journey from a bronco to a slide which is controlled by a Second World War gas mask isn't a long journey, and it raises other interesting things. So I want to actually kind of make another point that's presumptive in NUIs, is that NUIs represent a kind of removal of artifacts and tools in the world, but tools themselves can be quite natural in use. So one of the ways in which we've actually used some of the techniques that are in NUIs is actually to use vision and vision tracking. So here, we're tracking torches on a surface, and based upon where the torch shines on a surface, we play audio tracks, and we've installed these in a range of different museum settings to overlay and give interaction. The point here being that it's the tool and the tool's context and use that makes it natural. It's not the removal of the tool or the hiding of it. So it's simply a torch being used in this way. I want to kind of end with a very kind of simple clip, though, which comes from a piece that comes from a shopping mall. And I'm going to show you a clip of my daughter when she was 17 months old, and show you that there is actually some powerful things. So there's a very simple projected surface on the floor of a shopping mall, and this is her first encounter with it. So it's kind of intriguing, isn't it, that she's able to do that, she's able to drive that. The rest of the evening, when she continued to do this on other surfaces, was equally interesting and actually a bit disappointing for her often. But it's interesting in that there is something engaging in that, and engaging and spontaneous in that kind of feedback. And I think can I end with just a dead simple grumpy message? And my grumpy worry about NUIs is that they're a license to kind of sprinkle in an indiscriminate manner sensors throughout in the world, to the point where we're scared to move, scared to walk, and have to think carefully about the clothes we wear in order to be hygienic.
Thank you, Tom. And to quote Douglas Adams, let us now bow our heads in payment. Yes, so I'm very much one of the people to whom Tom would object. I'm very much technology-driven. I've been interested for a long time in recovering three-dimensional data from imagery of the world. And one of the ways, when I worked at Oxford, that we demonstrated this was to take videos, such as the video you see there, recover the three-dimensional shape of the scene, and then prove that we'd done that by placing this dancing 3D object in the scene. And that was successfully spun out by Oxford Metrics and by Nick Bolton, who I believe is in the audience somewhere, and won an Emmy Award at some stage for its contributions to making television easier for us all to enjoy. Whether or not you agree is another question. Since then, I've been interested in doing the same sort of thing, but now instead of a still world, that world was static, it was just buildings, I have a moving object which is changing its shape, and again I demonstrate that I know something about 3D by placing moustaches and other decorations on the face of the moving 3D object. And my recent work then has looked at this I can do from video with small amounts of motion. I was interested, of course, obligatorily, an interesting type of deforming 3D object is the human body. So I've introduced this picture of some work we did a few years ago in trying to track human motion. The character on the right is following the movements of the black-suited person on the left. And this is interesting, I think, because as Jamie will tell you in a second, there was almost no contribution from this work to that which eventually made Kinect work. This was Blue Sky's research, which proved to have no use in practice. And we hadn't solved the footscape problem at that stage, so his hips are locked. And then most recently, I've been interested in large amounts of deformation. So if I type dolphin into an internet search engine, I will recover a sequence of images like this. As humans, you, even if you'd never seen a dolphin before, might have an idea that there are a family of types of 3D shape that gave rise to these images. So we've recently, after quite a long period of research, managed to write an algorithm that can reasonably reliably recover just from those images a family of 3D shapes, and it's demonstrating that here by overlaying a different shaped 3D dolphin on each of the instances in the data set. So I'm very much about what sensing techniques we can use to enable natural user interfaces, but I hope I learn from Tom that they don't need to be used everywhere. Thank you. Jim.
Thanks, Andrew. So I'm going to give you a very brief whirlwind tour of visual object recognition from photographs to Kinect. So about 3 years now, we got a call pretty much out of the blue from the Xbox incubation group, who were working on a product that turned out to be something we all know as Kinect today. And as Andrew showed in his example, what we're trying to solve is the problem of tracking the human body, tracking the motion of 20 different joints in your body in real time as you move. And they came to us and they said, well, can you help us? These are the problems we need to solve. It really needs to work for everyone, no matter what position you put your body in, no matter your shape and size, your weight or your height, for example. It has to be incredibly reliable, and it has to sort of just work. You sort of jump in, and it recognizes you, and you can just play straight away. And it has to run really fast. So this sounded a bit of a tall order. One thing that gave us some hope was the camera, the amazing new depth sensing hardware. So this camera, unlike a normal photo camera that just takes an image where the pixels contain red, green, and blue, they contain color information and intensity. The depth sensing camera can tell us the depth away from the scene, and that deals with all sorts of problems like variable backgrounds, for example, and the different colored clothes that you're wearing. But it doesn't really give us an interpretation. So what could we do? Well, the reason they had got in touch with us was some of the earlier work we had done. So about 6 or 7 years ago, the Machine Learning and Perception group here in Cambridge had started on a very much blue skies research program on object recognition. So in this example here, I'm showing some results where the computer has learned, using machine learning, to classify each pixel to tell us automatically which category of object that pixel belongs to, and to thereby segment the image and delineate these objects from the foreground from the background and the other objects. Now, well, if you would ask me back then what was this useful for, I probably would have had to sort of scratch my head for a little bit before making up some answers. But as we've already seen with Antonio's work on medical imaging, that's one avenue of application this is proven very useful for. And the other is Kinect. So how could we specialize this for Kinect, for the tracking of the human body? Well, it's machine learning, so we're going to need some training data. And this is going to give you a hint of how we do it. So we start with our images of people, and we divide the human body up into about 30 different parts. And we're color coding them here. So you can see as the person moves, these colours are meant to follow their body. And you'll see there's different shapes and sizes, different human poses. If I play this video of a deep zoom image of all of the training data we generated, you'll start to see the variation in all of the human form that's in there, all of the different shapes and sizes, different poses. And as you'll zoom out further and further, you'll start to see the scale of this training data set. There's actually 1 million images there that we're having a look at. Now, if you take this data, now, fortunately, because we have a depth camera, we can simulate this data using computer graphics. If we take that data, there's 1 million images, do our machine learning number crunching, then we can end up with a really compact, fast system that can be used for real-time human pose estimation. So let's see this in action. Okay, so what I'm bringing up here is, you can see it on the screen here, and we've got it on the TV in front of us. What you're seeing here is this body part classification, this body part recognition running in real time. So as we move around from side to side, move our limbs around, you can see that these colours are following our motion as if we were wearing coloured suits. And this is because it's been shown so many different examples of the way that the human form looks like. And if we can do this 30 times a second for 2 players, then what we can do is summarize this information that we're getting at every pixel into just hypotheses about where the different joints in the body are. So that's what I'm showing here now. So this is just a summary of those colored suit representations. And this, as you can probably guess, gives us a really good hypothesis about the positions of the different joints in the body. Now, this isn't the whole story, and there's a whole lot more exciting work that goes on top of this and engineering magic that the Xbox team put together. But this gives us a really good starting point. And it's instant on. It's, every frame is dealt with independently, so you don't have to worry about starting in a particular starting pose. So thanks very much, Gareth. Cheers. And there's just a few more examples of the results that come out of the system. And you can see that even though there's no tracking going on, it really does look very smooth and coherent. So with that, I think I'm going to pass on to Shahram.
Thanks, Jamie. My name's Shahram Izadi. I'm a researcher in the Sensors and Devices group. Primarily and broadly, my research is centered around pushing the boundaries of how we interact with computers, and in particular moving away from mouse and keyboard for interaction. And a big component of that is actually on the sensing side. So I'm very much interested in new ways and richer ways of sensing the user and representing the user. So when I joined Microsoft in 2005, NUI, the term had just been coined, and it had a very different meaning back then. It was about direct interaction with touch screens rather than touchless interaction using the Kinect camera. And whilst a lot of people were looking at these forms of interaction, so interacting with your fingertips very carefully with these touch computers, and ultimately it seemed stretching photos continually. We were looking at more natural ways of interacting with these types of touch computers. And there's a few things to note here. So first of all, we're not interacting with flat graphics. These are 3D worlds that we're interacting with through touch. These worlds actually have some physical, realistic behaviors, and there's actually a physics simulation running in the background that's interpreting our touch and mapping that into a representation of real-world physics. And then the final thing is that most touch computers don't allow you to interact in this way. They don't have this richness of sensing. And so we had to actually develop our own, which predominantly meant ripping the back off LCDs, building our own electronics, such as these grid of IR transceivers in the top right corner, embedding them in the back of the LCD, and sensing the hands, for example, that are touching the surface in the bottom right-hand corner. It soon turned out that touch is limited to 2D, so we started to experiment with 3D touch computers. And this was around the time that depth sensing cameras were emerging. This is actually a 3DV camera that we're experimenting with that allows us to go beyond the surface in terms of interaction. We can actually lift objects off the touch screen and place virtual objects on top of one another. Beyond that, we started to experiment with output as well as input. So the ability for these types of surface computers to project through the surface using new types of screen materials. In the example on the right, you see a switchable diffuser. This is a special type of projection screen that can switch between two states, clear and diffuse, frosted so that you can project onto it. It can do this very quickly, so we can switch it at a rate that is imperceptible to your eyes. So you see a persistent image. But then we can project through the screen a completely different image onto this sheet of paper that we're tracking through stereo cameras through the actual display. Beyond this work, we've started to now experiment with Connect. Connect is a great enabler for new forms of user interaction. It's a rich sensor, but it actually provides a lot of challenges as well as solving a lot of challenges. So in the bottom right-hand corner, you can see a room that we've augmented with 4 fixed Connect cameras, and you can see a user trying to interact within this room with the virtual objects, and actually dancing around the room in interesting ways to interact with these virtual objects. So what we're doing here is actually fusing the data from the Connect cameras into a single representation. But that representation is still fairly coarse. You only get a sense of the primary or the dominant surfaces within the room. And the final piece of work I'd like to show is actually using a moving Connect camera to allow us to actually get finer grained capture of the user and the environment. And for this, the project is called Connect Fusion. I'd like to introduce Richard Newcomb on stage. Richard was one of the lead collaborators on this project. He's at Imperial College and he interned with us. And if we switch inputs over to the demo PC, and if I maximize this, so you can see as Richard is moving the camera, what we're doing is capturing lots and lots of depth data using the Connect camera, and we're fusing all of this depth data together to create a 3D model on the fly, a 3D model that could be used in computer games or CAD, so on and so forth. If I actually switch over to another view, as Richard is continually capturing, this is a third-person view of what you're actually seeing. So here you can get a sense of not only the fact that this is a 3D model that we can zoom into the desk here, for example, but you can actually see what's happening in terms of the underlying technology. As Richard is moving this camera, the 3D pose of the camera is being predicted frame by frame just by looking at the depth data that we're getting from the Connect camera. So no other infrastructure, no other types of sensing. Once we have a prediction of the pose, we can start to integrate this data into a single volumetric surface representation. And essentially what that means is that we're fusing this data over time and refining our 3D model over time as we're capturing more data from different angles. And this gives us an effect almost like image super resolution, where you're really starting to see fine details on people as we're capturing more and more viewpoints. So we were going to finish with a 3D scan of Gareth. Gareth, would you mind being a guinea pig? So great. I can just switch over to the main view. So we get...
I had a big lunch.
So you can see the level of detail you get over time. We can start to look at the creases on your trousers or your shirt. level of detail that you wouldn't be able to get with other types of reconstruction systems at this speed. And now this is a £100 sensor that actually allows you to do 3D scanning in the home very, very cheaply. So that's Connect Fusion. Can we have a round of applause for Richard as well? Thank you. And I'm going to end there. Thank you.
Okay, well, a round of applause for all four of you whilst we're all... That's great. So just before we go and hand over to Andrew to wrap proceedings up, a quick thought maybe from the four of you, if you each want to venture a reply to this. Tom will probably give us a grumpy reply as well. But is this is this the end? With this gesture recognition and so on, the end of the mouse and the keyboard as we know them as input devices.
It will join that kind of obsolete pencil, the keyboard and mouse replace. So I mean, obviously, tools are always going to be existing. They're going to be used in particular niches, and this is another armoury of input and output for me. And I think there's some interesting challenges for me, because I was trying to think about. So I can see this technique useful in fairly surface interactions and browsing. What happens when you're kind of writing code? You're doing something complex and deep, and that requires a lot of stuff, and where the representations of text and other representations are really critical to the task. And I'm kind of intrigued as to just how far as an interface and interaction technique this stuff starts to go.
Yeah, it's a great question. We get it asked a lot. Is the keyboard and mouse going to go away? If you can see on my side, of course not. I'm using the mouse and keyboard, and I'm doing that specifically for writing code. So input devices are good for certain tasks. And when it comes to long-term interactions with a computer and very fine interactions, the mouse and keyboard is probably the right type of input device. The types of rich or expressive gestures that we're looking at with Connect or with multi-touch lend themselves to other activities, sometimes more playful activities. So everything's good for something and bad for something else. And we're not going to replace the mouse and keyboard, we're just merely going to augment it.
Okay, so quick responses from Jamie and Andrew, otherwise we'll crash the news. So just brief responses.
I agree with Cleggy here.
Very brief.
Yeah, I totally agree with both of you. They're not going to go away. I think one thing we could add, though, is that what we're seeing with Connect is the ways in which people are able to have so far used Connect and touch-free interactions have only just scratched the surface of what's going to come in the next few years.
Okay, right. So agreement and accord breaking out, but we haven't had a drink yet, so that's probably why. So, okay. Well, thanks to the four of you and to all the other researchers that we've met this afternoon, and also to Microsoft Research for quite a roller coaster ride over these last 20 years. So I'm the outsider here, but even I'm certainly looking forward to the next 10 years, next 20 years, and I'm sure decades beyond. So thanks to all of you for having me this afternoon. It's been a fascinating afternoon for me. And we're just going to wrap up with a few words from Andrew. So let's take the stage here.
Well, thank you all for coming. It's been